All right, drawing free body diagrams. So when we are wanting to see how an object is going to move, we know that once we know its acceleration, its initial velocity, we can find out for a period of time or for a certain distance the other variables. Now these accelerations are always caused by only one possible thing, by Newton's second law, a force. And so if an object has more than one force acting on it or has several forces acting on it, and we want to predict what it's going to be doing, we analyze the situation first by making what's called a free body diagram, and then use the free body diagram to make equations using Newton's second law. That is the equation. So let's say if I have an object sitting on a table. Well, what are the forces acting on this object? There's gravity pulling it down. So the rules of the free body diagram, the first rule is object is represented by a dot or something like it. Okay, so generally people will just say, okay, here's the object. It's just a dot. And the second thing is only forces are shown as vectors. Okay, that's the only thing we're going to put in there. We're not going to write down the velocity or the position or any other feature of this object other than forces. That's the only thing that shows up in free body diagrams. Forces point outwards. Okay, so if I'm even pushing this box this way and I want to make a free body diagram, I would not show the force coming into the object, but rather being applied in that direction. Always the arrows pointing out of the object, okay, always coming out, nothing, never going in. And label each force and draw in proportion. Okay, so now this object here, forget about this little thingy I drew here. It is sitting, so it has two forces acting on it. We know gravity is always acting on it. That's the one you can always pick. It's going to be always acting downwards. And then we have one more force acting on this, which is the normal force, which is preventing this object from going through the table, because it's always being pulled downwards. So that object that's supporting it, Fn, they're meant to be in a straight line, I just didn't get it right. And so, and then make Fn the same side as Fg to kind of show that they're equal. Well, that's the free body diagram for that object right there. Okay, well, let's have some more fun with this object. Let's say that I have an object hanging from a cord. The free body diagram of this looks just like the one on top, except for the labeling. We again have gravity acting downwards. And yes, you guessed right, tension acting upwards. Okay, Ft. And these are also equal in size, showing that, you know, the object is basically in either constant motion or not moving at all. All right, meaning it's not accelerating, okay? Let's look at a guy hanging from a pole. What are the forces acting on this body? And so we have the force of gravity pulling him downwards, And it looks like we have two tensions acting upwards, which you can draw as FT, FT, making sure that these two add up to about the same size as this. Or alternatively, you could draw it like this. Okay. Generally, you'll see them done this way. All right. Let's start looking at another thing. How about we drop something and it's falling? Well, there's only one force acting on it. It's the force of gravity. That's it. Okay, how about the egg is falling, but there's air resistance. So the egg is falling. So we have the force of gravity, of course, acting on the egg, like it always is. Everywhere it's just the force of gravity. And then the egg is still accelerating, but not as fast because there's a little bit of air resistance. So I'll put FD, or you could write that as F air. D is for drag, or air for air resistance. Okay, simple explanations. Let's start looking at something more complicated. A skydiver has jumped off a plane, and he's moving really fast now, and he's moving so fast that the air resistance is as the same size as the force of gravity. And so after accelerating for a while after jumping off the airplane, he has now reached a speed where gravity is still pulling him down the same amount, but there's an equal force to the force of air resistance, which increases more and more the faster you're going. If you've ever experienced, it's like your hand out of the car in the window, and you feel the force pushing it back. Well, double the speed of the car, and the force won't be twice as much, it'll be 4 times as much. It actually goes by the square of the velocity. Anyway, for it, it would look like Fg and F air both being the same size. Okay? Now let's look at some more, a little more complicated problems. So here, let's look at an object hanging from a string this way, and then another string over here. Okay, so it's an object that's suspended in the air. We have a force pulling it this way, tension, a cord, or a rope, and Ft2 over here. And so what would the free body diagram for that look like? Well, you have Ft2 here, Ft1 here. Now note, if you know that this angle is, say, theta, then you would put that angle up here as well, showing theta. That's the angle at which it's at. And then you'd have mg, or force of gravity, which is the same as mass times gravity, force of gravity acting downwards. And so that would be the free body diagram for this. Note, I'm only showing forces. Okay. And the angle that they're at, because that's important, because remember, this is a vector. So if an angle is given, that needs to be determined. Otherwise, we just assume it's all in the x or all in the y. How about an inclined plane? First, let's do an inclined plane with no friction. Well, if you look at this object, we have the force of gravity acting downwards. The normal force always acts at 90 degrees to the surface, so they would be acting somewhere up there. Made that a little too long. Normal force would be acting this way. Okay? And really the component of the normal force, which is in this direction, of gravity, which is in this direction, if I make my axis in this way, And so if this is my axis like this, then the normal force is acting in that direction, in the y direction, and so this component of gravity, which is now no longer exactly down, but in this new coordinate system is down this way, you would have this roughly, this component of gravity must equal the normal force here because it's not accelerating this way, but it will accelerate down without friction. But just to break that down, your free body diagram would just be this. Okay? And notice when we add our vectors head to tail, if I were to take this vector and put it down here, I would get an arrow, a net force acting this way. I'm adding the two vectors. Remember, sum of the vectors is equal to mass times acceleration. Then that'd be the acceleration down in the same direction in which this goes down. All right. Next thing that I want to go over is looking at free body diagrams with friction. So we use F of F for friction. And so if I have an object here and I'm pushing it and it's moving at constant speed. I call the force that a human applies, or a person applies, or an animal applies FA for F applied. And so the free body diagram for this, you would have F applied in this direction, and the force of friction in this direction. And the force of friction, if you remember, is going to have to be the same size as the applied force because it's moving at constant speed. That means I'm pushing it with just enough speed to overcome friction, or just enough force to overcome friction. And so it would be moving at a constant speed, no acceleration because of that. Don't forget our normal force, which is still acting upwards, and our force of gravity, which is acting downwards. So there it is for an object being pushed to the right with a force equal so that it's moving at constant speed. How about an object that is being applied with a force and is accelerating? Means I'm pushing it beyond the force of friction and to make it go faster than that. So my free body diagram looks similar for Fn and Fg, again, both being the same size. But this time my force applied will be larger than the force of friction. And so there's a free body diagram for that situation. Let's look at one where a block has been pushed and is sliding to the right and is sliding to a stop. Okay, what would the free body diagram for that look like? If you want, you can pause the video and try to sketch yours. Okay, so here's my dot. I'm going to put in these guys right off the bat. And now I'm not applying any force in this direction. This was moving in that direction and it's skidding to a stop because of friction acting in the opposite direction. Okay, friction opposes sliding. So whenever this is sliding this way, the friction force is going to be in the opposite direction. So we have friction acting here. And you might be tempted to add another one, but that's it. There's no other forces. So this object is moving in that direction with a force acting in that direction, so it's going to eventually come to a stop. Once it does that, it'll look just like this. Okay? Well, that's it for free body diagrams for now.